Hi and welcome to this video tutorial on gears. On a mechanical aptitude test, it's not uncommon to find a couple of questions relating to gears. Gears are a system of interlocking wheels that can produce massive amounts of mechanical advantage. How much mechanical advantage depends on the gear ratio, or the relation in size between the gears. But before we get too far, let's go ahead and take a look at something simple first. This is a standard gear question. If A spins right, B spins left, and C spins right, which way will D spin? There is a very easy trick to determine the answer here. If the number of gears is odd, it spins the same way as the first, A. If the number of gears is even, the final gear will spin the opposite way of the first. Make sense? Problems like these are simple when you know the shortcut. Closely examine the accompanying image. If gear A runs to the right, which direction will gear D turn? Now let's see a more complicated version of the same thing. Using the same image as the previous question, if gear D has twice the diameter of C, what is the mechanical advantage of D? How many revolutions will C make for every revolution of D? There are two questions related to this image, so let's take them one at a time. First, mechanical advantage. Since we can say gear C is the input gear as it turns the D gear, and our input gear is 1/2 the size and has half the number of teeth, our mechanical advantage equation is as follows. Mechanical advantage is equal to the teeth of the output gear over the teeth of the input gear. In this case, it's 24/12, which means we have a mechanical advantage of 2. Now let's examine the gear ratio and find how that impacts how much turning these gears will do. Gear ratio is similar. Since we know that D has twice as many teeth as C, the ratio of driving gear to the driven gear is 1:2, meaning that for every rotation of C, D only revolves 1/2 times. Make sense? Now for a couple of fun ones to try by yourself. If gear A spins to the right, which direction will N spin? To the right or to the left? In this case, there's an even number of gears, so if we use our simple little cheat, it means it's going to go to the opposite direction of the first one, in this case, to the left. Last one. The smaller gear has 12 teeth and the larger gear has 24 teeth. If the small gear turns 12 times, how many revolutions will the larger gear make? The answer here is C, because we know the ratio is 1:2, which means the larger gear makes half as many turns as the smaller one. Half of 12 turns is 6. I hope that helps. Thanks for watching this video tutorial. Hi and welcome to this video tutorial on horsepower. Knowing a little bit about horsepower can be incredibly helpful in a mechanical comprehension exam. There are multiple ways of defining 1 horsepower, all of which are rates. The most commonly used terms are electrical and mechanical horsepower. First, electrical horsepower refers to an amount of joules created per second. Instead of saying joules per second, however, we can simply say watt or watts. 1 electrical horsepower is 746 watts, or joules expended per second. For mechanical horsepower, we're talking about how much force it will take to move 1 pound, 1 foot over a period of 1 second. It is often agreed that 1 mechanical horsepower can do 500 foot-pounds per second of work, or 33,000 foot-pounds per minute. With that knowledge in mind, let's go ahead and try a couple of practice problems. First, something really easy. The power needed to move 550 pounds 1 foot over a period of 1 second is commonly referred to as what? A joule, B, a watt, C, a torque, or D, a horsepower? Obviously, the answer in this case is D, 1 horsepower. Now let's take a look at something a little bit more realistic, closer to something you'll see on the test. Jack needs to pull a truck for 1 minute. The truck weighs 115.5 tons. What's the minimum number of horsepower necessary to accomplish this? A, 3 horsepower, B, 7 horsepower, C, 21 horsepower, or D, 420 horsepower? The answer is B, 7. Here's how we got the answer. First, we multiply the number of tons by 2,000 pounds. This will give us the weight of the truck in pounds. Once we have that, we divide by 1 horsepower, or rather the work that can be accomplished by 1 horsepower, which is 33,000 foot-pounds per minute. So, having done that, we have 7. An elevator motor requires 5,968 watts to move the elevator. What is the horsepower of the electric motor operating the elevator? A, 7, B, 8, C, 13, or D, 746? To find our answer, all we have to do is divide the number of watts produced by the motor by the number of watts that we know a horsepower can produce, 746. That leaves us with the answer 8, B. I hope that helps. Thanks for watching this video tutorial. Welcome to this video tutorial about liquids and hydraulics. Mechanical comprehension exams often require you to have a basic knowledge of liquids and how they're harnessed in order to produce mechanical systems like hydraulics. There are some basic rules of physics that you need to know, although these are simplified because tests don't usually require you to know the minute details. First, liquids are incompressible. Second, liquids always conform to their containers. Third, an enclosed liquid, when pressure is applied, equally distributes that pressure. Another thing to know is the equation for pressure. Most simply, pressure is equal to force over area. For water specifically, there's about 0.43 pounds of pressure per square inch for every foot of water depth. Thus, the amount of pressure at the bottom of a 12-foot pool is approximately 5.2 pounds per square inch. Given the rules above and what we know about pressure, let's look at a few examples. Here is one that displays the basic function of a hydraulic system. On one side is a vat of liquid, which is connected by a hose to another vat. If the left vat is pressurized to move the liquid down 1 inch, how much will the water level in the other vat rise, assuming they are the same size? Because of the rules that we mentioned before, especially because pressure applied to an enclosed liquid is equally distributed, when the liquid on the left vat is pressed down 1 inch, the water level on the right vat will rise exactly 1 inch. Another example. Here are 2 vats again. The left one is half the size of the one on the right. In this case, if the pump on the left moves down 2 inches, the one on the right will move up 1 inch. That's because the mechanical advantage is such that only half the force needs to be used on the left, but it needs to be pushed twice as far. Let's try another practice problem. Imagine a diver is practicing diving in the bottom of a diving pool, which has a depth of 20 feet. Where is the water pressure greatest? Where the diver is? Halfway between the bottom and the surface? It does not matter, because water pressure is always equal. The answer is A, because water pressure increases by 0.43 pounds per foot, if you remember. B is wrong because the surface has almost no pressure relative to the depth of 20 feet. C is wrong because water only equally distributes pressure when it's in an enclosed and pressurized space, like a hydraulic tube. One more practice problem. 2 identical enclosed containers of liquid are connected by a pipe. If one side receives 12 pounds of force, how much will the other side receive due to the connecting pipe? A, 1 pound. B, 6 pounds. C, 12 pounds. D, unknown. The answer is C, because the containers are equal in size and are pressurized, so therefore they will distribute weight equally. I hope that helps. Thanks for watching this video tutorial. Hi, welcome to this video tutorial about power, friction, and inefficiency. We know that whenever we work, forces act against us. For example, when I try to push a box across a floor, There's this thing called friction that makes it more difficult than simply pushing the weight of the box, because I'm pushing the weight of the box and the resistance of friction. And when the weight of the box increases, so can friction. This means I'm not as efficient as I could be. The same is true for engines and other things. That's why we add oil and lubricants to make the friction decrease and our efficiency increase. Sometimes questions about friction and efficiency end up on our mechanical comprehension exams. So let's be ready and try a couple of practice problems. Imagine you're using a pulley system to lift a box that weighs 100 pounds, but the pulleys are only 50% efficient. How many pounds of force are you actually putting into moving the box? Here's how to solve one of these. Just divide power output by efficiency. Here, our power output is 100, and efficiency is 0.50, or 50%. Thus, power output divided by efficiency is equal to 100 over 0.5. And now we know our initial force, which is 200 pounds. Make sense? Here's one to try by yourself. An engine produces 90 horsepower and is 90% efficient. So how much horsepower is being lost because of inefficiency? Remember, the output is placed over the efficiency. 90 horsepower over 0.9 in this case. That's equal to 100 horsepower. And that is what the engine would be on total efficiency. But the question is asking how much is being lost due to inefficiency. So we subtract 90 horsepower output from the 100 horsepower, which would be the 100% efficiency. And we end up with 10 horsepower. 10 horsepower is being lost due to inefficiency. I hope that helps. Thanks for watching this video tutorial. Hi, welcome to this video tutorial on pulleys. Mechanical comprehension tests often address pulleys, so it's important to understand their advantages and how they work. First, let's start with a simple fixed pulley system. A fixed pulley is when a rope or chain or something similar is wrapped around a wheel or axle in order to raise or move a weight, like this. In this case, the wheel or axle simply changes the direction of the force exerted to move the weight. This all changes when a double pulley or block and tackle system is used. When multiple pulleys are used, their mechanical advantages increase and the weight becomes easier to move. Here we have a block and tackle or movable pulley system. One pulley is still fixed, in this case to the ceiling, while the other moves with the object itself. Here we can see the force exerted by someone pulling with 50 newtons. That force goes around the pulley and acts on the weight, but then it goes around the second pulley, once again acting upon the weight. That original 50 newtons of force acts towards raising the weight every time it circles the pulley. This provides a significant advantage, as you can see here, since the person pulling can raise a 100 newton weight with only 50 newtons of force. Of course, in these examples, and likely many of the problems you will see, friction is neglected. This all means that a four-legged pulley system is equal to 4 times the original force exerted to move the weight. Mechanical advantage of a four-legged pulley system is equal to 4 times the original force exerted to lift the weight. The equation to find out how many times the rope should wrap between the fixed block pulley and the movable pulley is the same equation used to find the mechanical advantage. Here, MA equals mechanical advantage. W equals weight. T is equal to tension, or the force used to pull. And N equals the number of legs, or times the rope travels between the two pulleys. Let's try an example problem. The man on the right is trying to lift this large package. The package weighs 200 pounds. How much force does the man have to exert in order to move the package upward? I'll give you a moment to try to figure out by yourself. Here's the answer. First, let's take a look at the mechanical advantage for this pulley system using our equation. It looks like we have a mechanical advantage of 2, because in this case, n is equal to 2. So that means the force of the man's pull will be doubled, yet even that won't be enough to lift the 200-pound package. In this case, the answer is no. The man will not be able to lift the weight even if he pulls with 80 pounds of force. I hope that helps. Thanks for watching this video tutorial. Hi, welcome to this video tutorial about levers. Levers are the most commonplace of all the simple machines. From shovels and knives to wheelbarrows and baseball bats, levers are everywhere we look. There are several components that every lever has, so let's go over and review those. Every lever must have a fulcrum, a point at which the lever rotates, a resistance, the force acting against the effort applied, and obviously the application of effort to move the lever. There are three classes of levers. They are differentiated by the positioning of the fulcrum, resistance, and application of effort. In a first-class lever, the fulcrum is between the effort and the resistance. A seesaw is a good example of a first-class lever. When effort is applied to force one end of the lever upward, the end where the force was applied must go down. Like a seesaw. The shorter the distance between the fulcrum and the resistance, the easier it will be to move. This is a result of the mechanical advantage, but we'll get to that later. Second-class levers is where the resistance is in between the fulcrum and the effort, whereas a first-class lever is able to increase force and distance through mechanical advantage. A second-class lever is only able to increase force. A common example of a second-class lever is the wrench. The force exerted by your hand at one end of the wrench is magnified at the other end. Basically, with a second-class lever, you are producing greater force at the other end. In a third-class lever, the force is applied in between the fulcrum and the resistance. A baseball bat is a classic example of the third-class lever. The end of the bat, where the ball is struck, is the resistance. By exerting the effort at the base of the bat, close to the fulcrum, you are able to make the end of the bat fly quickly through the air. Now that we've defined all three classes of levers, I'm going to show you a series of images. Now I want you to identify each one of these images as a certain type of lever. Let's get started with this first image. What is it? First, second, or third class lever? That's right, second class lever. Because the resistance is in between the fulcrum and the effort. Here's another image to identify. This is a third class lever. Look at where the force is applied. It's in between the fulcrum and the resistance. Like a baseball bat, this is a third class lever. I hope that helps. Thanks for watching this video tutorial. Hi, welcome to this video tutorial on work. In science, we say a force accomplishes work when there is a displacement at the point of application of that force in the direction of that force. Now, if none of that made sense to you, don't worry, I'm going to explain. The unit of measurement of work is the joule, which is the force expended in newtons times the distance traveled in meters. So, for example, imagine there is a box in the ground. You go to lift it 1 meter off the ground. If you cannot get it off the floor, you have not achieved work. If, however, you do lift it 1 meter and expend 20 newtons of energy doing so, you have achieved 20 joules of work, because you lifted the box 1 meter using 20 newtons, and 20 newtons times 1 meter is 20 joules. Make sense? Let's try some other examples. If a rock climber expends 660 newtons up a 30-meter cliff, how much work did he exert? The answer is D, 19,800 joules, because we multiply 660 newtons by 30 meters. Let's try another one. A child uses 3.5 newtons to throw a ball into the air about 2.3 meters. How much work has she achieved? The answer is C, 8.05 joules. Again, we only have to multiply 3.5 newtons by 2.3 meters. So, as long as we remember that work is always going to be defined in terms of force expended to displace a body over distance, we will get the right units, usually joules. To find our answer, we simply multiply the force by the distance, usually newtons times meters. Make sense? I hope that helps. Thanks for watching this video tutorial. Hi, welcome to this video tutorial about wedges. Now, wedges are one of the most common simple machines, as they don't have any moving parts but provide a large mechanical advantage. As you are aware, the shape of a wedge is just a triangle, usually isosceles, so that the length of two sides are equal, like the example shown here. Sometimes objects called inclined planes are also used to the same effect. Thankfully, finding the mechanical advantage of these two objects is relatively easy. Take, for example, this wedge. It has a length of 10 units and a width of 4 units. The equation for finding mechanical advantage is MA is equal to L over W, where L is equal to length and W is equal to width. So in this case, we divide 10 by 4, which equals 2.5. The mechanical advantage is 2.5. Let's try another. In this example, we have a wedge that has a length of 21 units and a width of 3. What's the mechanical advantage of this wedge? Well, as you can see, it's just going to be 7 because we divide the length, 21, by the width, which is only 3. Make sense? Try a couple on your own. A wedge is 14 inches in length and the mechanical advantage is 7. What is the width of the tool? We already know that the mechanical advantage is 7, and we know that the length is 14. We're dividing 14 by something to get 7. The answer is 2. Now, if you're concerned about inclined planes, don't be. Like I said, they work almost exactly the same as a wedge. The mechanical advantage is similarly calculated as well. So here's an example. The length is 15 and the height is 5. The mechanical advantage is 3. 15 divided by 5 is 3. Let's try one more practice problem. A truck ramp is used for its mechanical advantage. If it's 18 meters long and 3 meters high, what is the mechanical advantage of this inclined plane? The answer is 6. 18 divided by 3 is 6. I hope that helps. Thanks for watching this video tutorial.